Hello friends, this is an introductory video on design of beams. In this video, we will see what are the load transfer mechanism in a beam, what are the different types of beam we have, what is the coping phenomena in a beam, and what is symmetrical and unsymmetrical beam bending. So let's get started. So if you see, we can basically transfer the vertical load from a structure to the ground. There are two ways. One way is by axial compression or tension, and another way is by using moment and shear. For example, let us consider I have to transfer the weight of 10% to the ground. So these are the persons and I have to transfer the weight of this person. One possibility is for each person we can provide a column. So this is a column here. Now the weight of the person will get transferred to the ground through column by compression. So in this case, column is under compression. So there is an axial force that is acting. So in this case, I can say the load transfer mechanism is axial load. So loads are transferred via axial load effect in the column. Now can we have another possibility by which I can transfer the load of these persons to the ground? Yes, we can have another possibility. In that case, what we can do is we can provide a beam, and on this beam these 10 persons can stay. Now if you see in this case, if you take any cross section, at this cross section there are two kinds of forces that are acting. One is shear and another is moment. And through this shear and moment effect, finally the weight of this person will get transferred to this column and finally to the ground. So you see in this case what is happening, the weight of these persons are getting transferred to the column via shear and moment effect. So we can say for a beam, loads are transferred via shear and moment load effect. What are the advantages of putting one beam in place of 10 columns? Major advantage is we are having this much space free, so we can utilize this space. And another advantage is we have an economical design. So first is one beam is more economical than 10 columns. Another is column free space is more usable. This means we can provide beam in place of column more effectively. So what are the applications of beams? One major application in bridges, we can have a straight beam, or we can have a curved beam, or we can customize the beam depending upon the situation. We can also use beam in a structure like buildings. We have a beam here and this is connected to a column. So this is a steel structure. We can also use beam in roof structures. So for roof, so these are the beams that we have used in this structure. This is also a beam. Now these beams can either be made up of wood, or it can be made up of steel, or even reinforced concrete. For example, in this structure we have reinforced concrete beam that is supporting the load that is coming from the roof. So with this we can define what is beam. So beam is a structural member subjected to transverse load, that is load perpendicular to its longitudinal axis, is called beam. So we can have different kinds of beam. For example, some of the typical beams are shown in this figure. So this is one beam, and we call these beams as floor beams. So these are floor beams. So we can call this as a floor beams. Now these beams are resting over another beam, and these beams are called girders. We also have some beam that is on the periphery or on the outer side, and these beams are called a spandrel beam, and this is another example of a girder. So this is also a girder. Only thing is these girders are along the periphery of the building, that is outer side of the building. So depending upon the location, we divide beams in different categories. And the first type of beam that we have is basically floor beams. And the floor beams are also called joists. So basically a joist is a closely spaced beams, and this supports the floors and the roof of the building. So any load that is coming on the floor or the roof of the building is basically transferred to the joist, or that is the floor beams. But important point, joist or floor beam does not support the load that is coming on any other beams. So this does not support the load that is coming due to the other beams. Another example we have, that is a girder. So basically a girder is a larger beam, and that is used for supporting a large number of joists. So if I have, these are the joists, and if these joists are supported by another beam, then we will call this beam as girder. And these are basically joists. So this is joist. Now similarly, we have spandrels. So basically spandrels are outer beam or exterior beam. So spandrels are the exterior beams at the floor level, and this supports two kinds of load, that is the load coming due to the part of the floor, or the load that is coming due to the exterior wall. So this supports loads that is coming on the floor, and this also supports load that is coming onto the due to the exterior wall. Similarly, we have a purlins, and the term purlins are often used in case of trusses. So whenever we have a purlins, this is used to carry the roof load that is coming in the trusses. Similarly, we have another kinds of beam, and this is often used in masonry structures, and this is called lintels. So for lintels, loads are coming from the masonry over the openings, and these are called lintels. So if I have any opening in the masonry structure, and whatever the load that is coming due to masonry, and here I can provide a lintel. So this is a beam that basically carry load that is coming from the top over the opening. Also we have a gut. So gut is a horizontal beam spanning the wall columns of the industrial building used to support the walls. So basically here I have shown an example of gut. So in this case, these are the guts, and that basically supports the wall in a horizontal fashion. So beams are supporting the load that is coming in the horizontal plane. Now we have discussed different types of beam. Then we can see what is the coping phenomena for a beam. This means how the different beams are joined and what kind of action I have to take so that the floor remains on the same level. So let's see this. For example, let's say I have a girder and I have to connect this girder with a floor beam. Now, if I want to make this floor level and this level on the same level, that is same elevation, then only one option I have, that is I have to cut this portion of this beam and then we can fit and then we can bolt. This phenomena, that is cutting off one of the floor beam, one corner or both corner, is called coping phenomena. So this is illustrated in this figure. Now if you see, this is I beam and in this case I want to fit at this position. So I have to cut this portion and this is a coping phenomena. We can cut both sides. We can cut this side as well as this side also. In some cases where I have to fit both constraint, that is I have to meet the requirement of matching the elevation from the both side. In that case I have to cut from both sides. So we can say cutting the corner of floor beam is called coping. The top floor beam and the girders are at the same elevation so that the floor deck can sit flush on both. So this is why we use coping of beams. Now the next question is how a beam bends under different kind of loadings. So basically the beam bending can be divided into three categories. One is symmetric bending, another is unsymmetric bending, and then we have a biaxial bending. So let's discuss symmetric bending. In case of symmetric bending, the loading plane must coincide with one of the principal plane of a doubly symmetric section. For example, a I section. So here I have an I section. In case of I section, there are two planes of symmetry. One is this one, let's call this as a x axis. Another is this one, let's call this as a y axis. So load either has to pass through x plane or y plane. For example, in this case, we have a I section and this beam is under the uniform loading. Now if I see this loading, this load is passing through y plane, and that's why this is a kind of symmetric bending. So what will happen in this case, this load will generate shear as well as moment, and under the influence of this moment and this moment, this beam will bend. So the next kind of bending is unsymmetric bending. So when the plane of loading does not pass through the shear center, and in this case bending is often coupled with torsion. So we have a bending as well as twisting. So this kind of bending is called unsymmetrical bending. We will discuss more about the shear center in the next few slides. But before that, let us illustrate unsymmetrical bending. So here I have a channel section. So channel section is symmetric about x axis. So this is a symmetric axis. Now we are applying a load W, and this load is passing through the center of gravity of this section. And under the influence of this load, this channel section is bending, and also this channel section is twisting. So basically bending as well as twisting both is happening in this case, and that's why this is an example of unsymmetrical bending. Now the question is why twisting happens in this case, and this can be explained on the basis of concept of shear center. So what is shear center? As I said in the previous slide, we have this channel section and there is a load W that is applied that passes through the center of gravity. Now if I consider any cross section of this channel section, for example, let us consider this section. If I cut a cross section, then it will look something like this. And we have already learned in the previous courses that in this case we will have a shear flow, and through this portion, that is flange portion, the shear will flow in this direction, and in this case from the bib shear will flow in this direction. Similarly in this case shear will flow in this direction. Now due to this shear flow, let's say F1 is the resultant force that is in the flange, that is in the bottom flange. Similarly the same force we will have on the top flange because of considering equilibrium, and we will have another force F2 that is passing through this bib. Basically F2 has to satisfy this W, that is F2 is equals to W. Now let us consider a point somewhere here. Let's call this point as A. This point is mid of this wave portion and lies on the x axis. So now if I take moment of all the forces about this point, let's point A, then this force F1, which is at a distance of h by 2, the moment will be F1 times h by 2. So F1 times h by 2, and this moment is in this direction. Similarly, another force that is on the bottom flange, again this will contribute F1 times h by 2, and this is also in the same direction. Now this force F2 basically passes through this point and it will contribute 0 to this expression. So I can say the total moment that is coming due to all these forces is nothing but F1 times h. Remember, we don't have to take the moment of W because we are considering this section, and effect of W we have already considered, that is the forces generated on this section. So now if you see the moment on this section, we have a moment that is F1 times h, and this will try to rotate this section or twist this section in a clockwise fashion. Now can we avoid this kind of twisting? Can we use some kind of mechanism to avoid such kind of twisting? Yes, we can. What we can do is we can provide a bracket at this position, and we can build this bracket, and we can apply this load W here. So let's say this distance from the center of the web is E. Now in this case, this load W will try to apply a moment that is anti-clockwise. If I take moment of this load W about this point A, we can write W times E, and this is the anti-clockwise moment. Now if I consider equilibrium of this section about this point A, I can write W times E is equals to F1 times H. So two moments can cancel each other, and finally we will have no twisting. So for no twisting to happen, this distance E is equals to F1 times H divided by W. So now we will call this point is a point of shear center, basically at a distance of E from the point A. So now if my load passes through the shear center, we will have no twisting, we will have only bending. So this is also illustrated in the next slide. So how we can make unsymmetrical bending to symmetric, that is there is no twisting. So we have to consider that the loading plane must pass through the shear center for a singly symmetric section or a channel section. And this is same is shown here also in this figure. So you have a channel section, and then we are putting a bracket at one of the end, and then this load W is passing through at a distance of E from the center of this wave portion. So this is about the unsymmetrical bending. Now we also have another kind of bending in beams that is called biaxial bending. So basically biaxial bending is characterized by simple bending with no torsion and occurs about both of the principal planes. So basically this is an extension of simple bending. Only thing is, in this case bending is happening along the two axes, but there is no twisting. So let us consider this simply supported beam, and in this case load W, this is applied here, and this makes an angle. So this is making an angle from the y-axis, that is y plane, and this is also making an angle with x-axis. So now this load W will have two components, one along this axis and another along this axis. Now we can analyze the two planes separately. So let us first analyze by z plane. So this is my z axis, that is along the length of the beam. So this is the z axis and this is y axis, and there is a force that is acting. So that is the force of this component, that is this force. So this will be W some angle. So let's say this angle is alpha. So this is W cos alpha. So basically, due to this force, this beam will bend something like this. There will be no twisting in this case. Similarly, we can analyze this beam for other plane, that is xz plane, and this load will come here, and we can again see the effect of this. So in summary, in this case, we can analyze two cases separately. That is, we are applying a superposition principle, and finally we can add these two to get the overall or resultant deflection or resultant bending of the beam. So to summarize, in this video we have seen what are the different types of beam we have and what are the different types of bending we have. We have asymmetric, unsymmetric and biaxial bending, and we also seen what is the coping phenomena for a beam. In the next video, we will see the different failure mechanism of a beam. Thank you.